Hi there, let's deal with our next topic, which is looking at earthquakes. We're going to focus in on understanding what they are, the different types of seismic or earthquake waves, how we measure them, how we might predict them, and how we can minimize damage to the earth. In order to understand earthquakes, we have to revisit plate tectonics again. We've learnt and talked about a few times already how the Earth's crust, even just below the ocean, is broken up into masses of Earth that actually float or move thanks to convection currents in the mantle. And this floating and moving is one of the reasons that earthquakes form. So what are earthquakes? Well, in general, it's a shaking or trembling caused by a sudden release of energy. And this release of energy is usually associated with something called faulting or the cracking open or breaking of rocks. And its continuingly adjustment of the position will result in aftershocks. We have something called elastic rebound theory, which explains how energy is stored in rocks. So let's take a fence here, and here's something called the fault line. What happens is when there's deformation in rock, the rupture will release energy and the rocks rebound to their original undeformed position, but as you notice, the fence now isn't lined up. Let's do some terminology here. The point within Earth where faulting begins is the focus, or another word, hypocenter. So wherever the energy was released as a consequence of rocks snapping or breaking, so it's usually below the surface of the Earth, we call that the focus. And the epicenter is the point directly on top of the Earth of where that snapping occurred. We use seismographs to record earthquake events. And so here's an example of a seismograph. It's the whole device that you see here. And then we usually use a marker and then a piece of paper, which is the seismogram. So what is it about earthquakes? At converging boundaries, the focal depth increases along a seismic zone. And so converging, don't forget, according to plate tectonics, plates that move towards one another are called convergent boundaries. And below the Earth, we get the snapping and therefore the elastic energy given off by the rocks. Where do we find earthquakes? 80% of them occur along the Pacific Belt, and most of these are at convergent boundaries. And so the Ring of Fire again. And there's a huge societal and economic impact in regards to earthquakes that we'll talk about. One thing that happens when earthquakes release their energy at the site of a focus, which is below the Earth, is they give off waves, P, S, and then surface waves, sometimes called L waves. So let's look at these P and S waves first. Here's a normal undisturbed piece of material. A primary wave or a compression wave will direct movement this way, and a secondary wave will cause the material to go up and down. P waves are the fastest moving, and they'll arrive at a seismograph first. They travel through solids, liquids, and gases, and like I said, they're like a compression wave. Picture a slinky. When you pull back a slinky and then let it go, that's like a primary wave. Secondary waves are slower than P waves. They travel through solids only, and they shear the Earth. which means perpendicular movement. And then L waves, sometimes called Love or Rayleigh waves, they travel along the ground surface. And so they look like this. They can cause the ground to kind of wiggle and woggle this way or go up and down like a rope. And they cause the most amount of damage to the buildings, even though they're the slowest of the three waves. Because, why do they cause the most damage? Well, look what they do to the ground. So how is an earthquake recorded? Well, P waves will arrive first, then S, then L and R. So here's background noise on the seismogram. That's the piece of paper. And then the first big squibble is the P wave. The second squiggle that you see will be the start of the S wave. And then the third squiggle is the L waves. Now we can record the time between the P and the S. And the difference in the arrival times can help us calculate how far away the epicenter is. So let's look at this. Here's the P wave, which arrives first at the seismograph, right there, cha-ching. Here's the second. The S wave arrives next. The difference between this can tell us how far away, how far away the earthquake is. So from there to there is the difference in time, which in this case is minutes, and then we can calculate the distance. 3 seismograph stations are needed to locate the epicenter, and so a circle where the radius equals the distance to the epicenter, and then so we make 3 circles, 1, 2, 3, and where they all intersect will tell us where the epicenter was. The size or intensity of an earthquake is relatively subjective, and so we've used in the past something called the Richter scale to help us tell how strong an earthquake is. And this is a logarithmic scale. Let's look at this again. So let's use some terminology. The focus is the spot where the rock actually snapped and gave off energy, and that's usually below the earth along a fault line where the plates meet, a fault line, plate margins. The distance directly to the surface is called the epicenter, and then where the rock snaps gives off these energy waves called seismic waves. And there are 3 types of seismic waves, from fastest. Again, here's a snap. There's the focus. This would be the epicenter. And again, earthquakes most generally occur at converging plates. That's plates colliding. Here are 3 seismic waves again. P waves, like the slinky. S waves, secondary waves. And L waves, which are surface waves. So fastest, second fastest, slowest, but cause the most damage. Here's the Richter scale. Again, it's logarithmic, which means it's on a 10 times. So if you go from a 7 to an 8 on the Richter scale, this is 10 times stronger. If you go from a 6 to a 7, that's a difference of 10 times stronger. So picture these all as 10 to the 8th, 10 to the 7th power, 10 to the 6th, and so on. Here's what a seismograph looks like. In the piece of paper here, the whole device is the seismograph, the piece of paper is the seismogram. Here's what a seismogram looks like. That's the piece of paper. So first we get the P waves, then we get the S waves, and sometimes we might get the L waves showing up. The time difference between the P and S waves usually indicates how far away the epicenter is. Earthquakes, like volcanoes, occur in a pattern around the world. If we mapped most of the earthquakes that have occurred over the last, I don't know, about 100 years, we'd notice that it maps out a pattern. And what is this pattern starting to look like? It's looking like the boundaries between all the tectonic plates, and especially where two plates are colliding or converging. Now, a tsunami is a very large sea wave that's generated by an earthquake. And so you get a crack in the crust below an ocean, and that heaves a whole bunch of water, which then comes to shore. Here's a picture of the big tsunami wave coming to Phuket. This was one of the biggest tsunamis that ever occurred, and it occurred in the Indian Ocean. And we could build what's called tsunami safe houses, which would help minimize societal and economic damage. This is facing the ocean, so water comes underneath and through the doors and underneath so it doesn't tear apart buildings. Let's look at the brain pop on earthquakes.
Did you feel that? No. Dear Tim and Moby, why do earthquakes happen? From Daniel. Well, an earthquake is caused by pressure deep within the earth. The surface or crust of the earth is broken up into about a dozen major and many minor plates floating on the liquid mantle. These plates are always moving a little bit. Sometimes they slide apart, slide together, or slide horizontally past one another. The active boundaries where plates meet are called faults. Depending on the type of plate movement on a fault line, you'll see volcanoes, mountains, trenches, and earthquakes. If it's that hard to snap a pencil, imagine how tough it is to break rocks. Over many years, moving plates build up pressure inside rocks. Tension strains rocks, just like Moby strained that pencil. Eventually, those rocks crack and shift to relieve the pressure. The rock breakage creates three types of seismic waves. P waves, or primary waves, are the fastest of the three, and they're the first to be detected. P waves are like sound waves. They compress and expand both liquid and solid rock as they move through it. Secondary, or S waves, travel at right angles to the direction of movement. They're the ones that cut rock. S waves can't travel through liquid rock, but unlike P waves, they produce vertical and horizontal motion. Surface waves are the third and slowest type of wave. They are also the most dangerous and can often knock buildings off their foundations. They move along the surface of the ground. These waves take the longest amount of time. Earthquakes can be so mild that you don't even notice them, or they can be strong enough to crumble entire buildings. Quakes are measured and recorded using a machine called a seismograph. A seismogram shows us how big the waves were and how long they lasted. Don't tell me you didn't feel that.